Let's jump right in. Welcome to The Explainer. I am absolutely thrilled to have you here today because we're diving headfirst into a cutting-edge theoretical physics research memo. And look, this isn't your standard dry historical overview. We are actively hunting for a literal missing link in our understanding of the universe. We're going to explore the bleeding edge where quantum gravity meets advanced topology and figure out exactly where human knowledge currently just stops and where a massive, totally unexplored frontier begins. So let's find that missing puzzle piece. To kick things off, what happens when you combine black holes with network math? I mean, it sounds like the setup to a sci-fi movie, right? But this is the central mystery we're unpacking today. We've got two incredibly advanced, completely mature fields of science that seem absolutely destined to overlap, yet somehow they haven't actually met. Here's our roadmap for the journey. 1. The search for new physics. 2. Universes as single points. 3. Causal diamonds and regions. 4. The mathematical network tool. And finally, 5. Finding the missing link. All right, let's get into it. Section 1. The search for new physics. Now, keep in mind the source memo we're looking at today isn't a textbook. It's essentially a live expedition, a detective story. Physicists conducted this deep literature review searching for a very specific mathematical crossover. They were basically looking for any evidence that anybody out there, had combined a specific theory of spacetime regions with a certain type of mathematical network analysis. And you know what they found? Completely uncharted territory. A massive, glaring gap between two highly established fields. Section 2. Universes as single points. So, to really grasp this gap, we need to talk about moduli space. In our everyday lives, a point on a map just represents, say, a city or a street corner. But in a moduli space, every single coordinate, every single dot on that map represents an entire shape, a complex space, or even a whole universe. It's literally a space of spaces. If you want to study how an entire universe evolves, or how different black hole shapes relate to one another, you actually plot them as individual points on this incredible mathematical map. And physicists have been building these spaces of spaces for decades now. Back in 1967, the Wheeler-DeWitt superspace mapped entire three-dimensional geometries. Then around 2005, researchers like Christensen and Crane introduced causal sites, arguing we should really swap out tiny fundamental point events for extended regions. By 2016, we saw generalized kinematic space mapping objects known as causal diamonds. And right alongside that, over in the math world around 2019, Hansen and Grist were formulating powerful new tools called Cellular Sheaf Laplacians. What we're looking at here is a massive paradigm shift. The old view basically treated spacetime as being made up of fundamental microscopic point events, like tiny pixels making up a TV screen. But the new view, it treats spacetime as being fundamentally made up of extended regions, whole three geometries, or these shapes called causal diamonds. The basic building blocks of reality in these modern theories aren't dots anymore. They're distinct extended shapes. Section 3. Causal diamonds and regions. Now, the real star of the show in modern holographic physics is the causal diamond. Essentially, it's an extended space-time region formed by the intersection of the future of one point and the past of another. So picture a flash of light expanding outward from a point in space and another flash converging inward to a point in the future. The overlap of those two light cones, that creates a diamond-shaped region of space-time. And this is the exact shape physicists are currently using to organize quantum information. And I want to be clear, this is not just some fringe idea. Entire mature subfields rely on this completely. Holographic kinematic space, Banks-Hilbert bundles and holographic spacetime, causal sites, black hole moduli spaces. All of these well-established frameworks use extended regions or causal diamonds as their fundamental organizing objects. They're already treating these complex shapes as the basic points on their maps. Just to prove how seriously the physics community takes this, check out this quote from de Boer and his colleagues back in 2016. They explicitly state that CFT degrees of freedom can be reorganized into observables living on the moduli space of causal diamonds. So the takeaway here is that physicists are already treating the moduli space of causal diamonds, that map where every dot is a diamond, as a real, continuous space where actual physics and differential equations happen. Section 4. The mathematical network tool. Okay, hold that physics map in your head for a second, because we're taking a quick trip over to the continent of pure mathematics to look at a very specific tool, the Cellular Sheaf Laplacian. I know, it sounds like a lot of jargon, but let's break it down. Basically, we're forcing the mathematicians and physicists to talk to each other today. Simply put, it's a highly advanced mathematical engine used to measure flow, connectivity, and data across a network. Imagine a social media platform where you want to measure how opinions flow and shift from person to person across different groups. A sheaf Laplacian is the exact math that lets you calculate that data flow over a structure. This Hansen-Grist spectral theory is a super mature, established mathematical field. It's successfully used on fixed graphs, cell complexes, simplicial complexes, data filtrations, and yep, even opinion dynamics on discourse sheaves. But notice the trend here. It is strictly applied to fixed combinatorial bases. People use it on traditional networks and datasets. Section 5, Finding the Missing Link. So, what actually happens when the physics continent and the mathematics continent collide? Well, this brings us to the massive aha moment of the memo. When they look at the crossover, the gap is glaring. Spaces whose points are geometries, established. Causal diamonds as points, established. Cellular sheaf Laplacians, established. But a sheaf Laplacian applied to a causal diamond moduli space, completely unexplored. We literally have the physics regions and we have the math network tools, but nobody has thought to apply those network tools to a network made of those physics regions? I really need to emphasize this point. Cellular sheaf spectral theory on region moduli spaces does not exist. The specific crossover of these two massive fields is entirely unestablished. It is quite literally an open door, just waiting for someone to walk right through it. And the best part? The memo doesn't just point out the gap, it hands us actionable steps for a brilliant new research program. Step 1. You take a region moduli space, like generalized kinematic space. Step 2. You choose a discrete cellular model of it. Step 3. You place a sheaf of local physics data, like quantum observables or entanglement data, right over that base. And step 4. You study the sheaf Laplacian spectrum to see exactly what it tells you about the physics of those regions. This is a literal instruction manual for a brand new subfield of quantum gravity. The literature review wraps up with its highly authoritative bottom line finding. The exact construction you describe appears to be genuinely underdeveloped or unexplored, not an established subfield. That confirms that this isn't just some minor oversight in the literature. No, it is genuinely uncharted territory, holding untold potential for whoever decides to map it out. Which leaves us with this final, provocative thought to wrap up our explainer today. If we actually take these causal diamonds, map them as a vast network, and run this advanced sheaf Laplacian mathematics over it, what new physics will it reveal? Could this be the exact puzzle piece we've been missing to finally understand quantum gravity? The tools are sitting right there, waiting to be combined. Thank you so much for joining me on this deep dive. Keep asking those big questions, and I'll catch you in the next one.